Hello everyone. So I'll get started. Today I'll be presenting on my work on capturing heterogeneous longitudinal changes in multi-wave ecological momentary assessment studies. So first, an outline, if you go to next, First, an outline of this presentation. I'll introduce a little bit about the multi-wave EMA study, and then followed by the data we collected from in our motivating example. And then I'll introduce the method we proposed, and then one empirical study and one simulation study to further illustrate the methods. And finally, we'll do the discussion. Okay. Before I start, I would like to acknowledge my collaborators and the committee members, because part of this work is from my my dissertation. So I would like to show my great thanks to my committee members who have provided very valuable feedback and suggestions on my dissertation. If you could go next. So let's first have a brief introduction of the multi-wave EMA study. I believe many of you are already familiar with the traditional longitudinal study, where participants are measured repeatedly over a long period of time. And the time interval between the time points measured is often like years. So we have longitudinal studies spanning over years. However, with the EMA study, it's like measuring participants more frequently, and it can provide you with with richer information about how participants' experiences change in their daily life or in their natural environment settings. And EMA studies is often conducted via some modern technologies such as the smartphones and wearable devices. So you can see that, so for instance, one EMA study focusing on participants' emotion may send the participants multiple surveys each day to evaluate their emotion level, and then participants will get their some prompts on their phones to answer these questions. So that's about EMA study. Different from a single wave EMA study, multiple wave EMA study involves collecting data across multiple time periods, such allows us to examine changes and trends of the changes over time. So here, as I noted here, we may have several waves for each, and in each wave, we measure the participants multiple times per day. And I want to add a note here that our definition of multiple wave is relatively broad. It may refer to waves with long intervals, which require several years to complete, like the traditional longitudinal study, or it can also refer to waves with shorter time intervals between them that are completed within a concentrated period of time, so that it can be finished like in several weeks or several months. Those are all in the scope of the current presentation. Okay, next. So here comes our motivating example, which is an intervention program on psychological well-being, or PWB for short. In this study, we have 160 participants who were randomized into 3 groups, the control and the 2 intervention groups. In intervention group 1, participants received the positive practices, which, for instance, asked them to think about for example, 3 good things that happened today. So the goal of these positive practices are to foster their gratitude, self-reflection, and social connectedness. And in the second intervention group, they received both positive practices and the contemplative practices. For the contemplative practices, we conducted mindfulness meditation, which helps them develop attentional control and emotional regulation, such lead to increased positive emotions. And here are some demographics of the participants in this study. And if you could go next. So this is the more detailed introduction of the study procedure. As mentioned before, we have 3 groups, control, intervention 1 and 2. And the only difference between these 3 groups are that for the control group, each day in the evening, they only receive some cognitive exercises. But for the intervention group, they receive positive or and both or the meditation practices. So this study consists of 4 periods. That is pre-intervention, intervention, post-intervention 1, and post-intervention 2. And each period consists of span over approximately 2 weeks. So in this case, I'm introducing type of multi-wave EMA study that without any time intervals between waves. I still regard this as a multi-wave EMA study because based on the broad definition, we call it multi-wave to highlight the intervention component intervention feature in this study, because the intervention may have already fundamentally changed some characteristics in people's psychological well-being dynamics. Yeah, so this is the introduction of our motivating example. If we could go next. Yeah, so you can see that we measure people very frequently. So we have very rich data. So what questions we can examine from this multi-wave EMA data? First, we can investigate the various type of characteristics of people's psychological or behavioral dynamics within each wave. Next, I will introduce the 3 interesting dynamic features that are of interest in turn. If you go to next, the first dynamic feature is baseline. So here in this plot, we basically plot the dynamics of the psychological well-being of one participant here. The x-axis shows the time and y-axis is the level of the psychological well-being they reported. And the baseline actually represents this person's average psychological well-being level, so that it will fluctuate, the dynamics will fluctuate around this baseline level. You can also understand this baseline as the mean level. And the other dynamic feature is intra-individual variability, or we can call it IIV for short. And it represents the variance, or how dramatically a person's PW level fluctuates. So here from this plot, it's kind of clear that in the pre-intervention, the variance is large, and then in the during and post-intervention, the variance is relatively small. And the next slide shows the third dynamic feature, which may not be very familiar to some of you, but is often studied in affective or emotion studies, which is called inertia or regulation. So here I'm showing a plot showing like with different levels of inertia, how people's emotion may change over time. You may see that, so first, inertia measures how quickly a person returns to their baseline levels after disturbance. In this plot, we can see that with the high inertia, if we look at the line with high inertia, that means people are more resistant to change. Compared to the low inertia line, this line shows that after entering the low emotion level, this person stayed in this level for a very long time, and it takes longer time for it to return to the previous level. So basically it measures how quickly or how resistant this person would like to change or return to the baseline level after some disturbance. And in this presentation, we'll use inertia and regulation interchangeably, such that high inertia will mean low emotion regulation. Okay, I think we can go to next. And besides the three interesting dynamic features we want to look at, because we have multiple wave data, we can also investigate the change patterns in these dynamic features across waves. For instance, there may be some increase in the baseline or regulation level or decrease in the variance level. And all these are indicators of a successful intervention. And there may be also some sudden shifts in the dynamic features. And in the following plot, yes, thank you. And in the following plot, I'll describe these changes and the different type of changes in detail. So this plot shows the dynamics of one outcome variable in our study. We chose meaning of life, which is one dimension of psychological well-being that captures how much an individual have a sense of purpose in life. And we chose 4 participants, 2 from the left 2 from the intervention group and the right 2 from the control group. We can see that there are very different change patterns in their dynamic features over time. Right? For instance, if we look at participant 1, there is a notable increase in baseline level or the average level from pre-intervention to intervention. And then this increased level stays even after intervention. And participant 2 also, the participant 2 from the control group also shows a gradual increase in their baseline level, although not very large and very obvious. And for participant 3, although it didn't show any notable increase in the baseline level, it shows some changes in their IIV or intra-individual variability. For instance, from pre-intervention to intervention, we see a reduction in the variance level. And then the variance increases again after the intervention. So you can see that in the 2 post-intervention period, the dynamics fluctuates more than the intervention period. And among these changes we have talked about, some of them are more gradual and continuous in their nature, and while others are more abrupt and discontinuous. Like for instance, participant 1 suddenly has a reduced IIV level from pre-intervention to intervention. And also participant 1 also shows some transitions between different levels of variance. And we call it regimes in this study. So that means participants 1 transition from high IIV regime to a low IIV regime, and then transition back to the high IIV regime. And all these type of changes, we wanted to model them. We wanted to capture them while still considering the individual differences in these changes. So that comes to our third research question. Next slide. Yeah, so individual differences in these changes over time. This is very important because it may provide some insights on like for whom the intervention works. And different people may show different change patterns over time after receiving the intervention. So by accounting for the individual differences, it allows us to understand for whom the intervention works. Okay, next. However, there are some modeling challenges there. First of all, as mentioned before, we need to accommodate all the heterogeneous trajectories. And then we introduced the 3 dynamic features before, right? However, most studies focus on only one or two dynamic features, and most often they are mean and variance, or mean and inertia in the emotion studies. So we want to have some methods that can simultaneously accounting for the three dynamic features. Third is that there is also a lack of research focusing on the simultaneous detection of different types of changes. As I mentioned before, some changes may show a gradual nature, and while some other changes may be more abrupt and discontinuous. And we wanted to model both. Finally, because there are just so many possible change patterns in people's dynamics, we may have a large number of candidate models that we propose to capture these changes. And so here we may need to have some diagnostic metrics to help aid the model selection. This is an introduction of our proposed model. We call it growth of hierarchical autoregression model, or go higher. Okay, yeah, I think there should be some animations, but I think I can introduce that in turn. So if you look at the AR model on the left, basically the AR model captured the three dynamic features, the baseline, the inertia, and the I rate. So mu is the baseline, and phi is the inertia, and the IV is the intra-individual variability. So this model helps model the dynamic features. And then we allow all these three parameters time varying by including growth curve models for these time varying parameters, like in the second chunk here. We chose a growth curve model because of the design of this study, which has 4 periods. And so we just, as a starting point, we choose a linear growth curve with period as the predictor in the model. And we know that growth curve models can capture individual differences, right, in their intercept and slope parameters. So that, for instance, in this study, we incorporated the group, gender, and age as predictors in the model for the intercept and the slope parameters to accommodate the individual differences in their initial levels and the growth rate. And then besides that, if people are also interested in capturing abrupt changes or possible regime transitions between in the dynamic features, you can also extend the growth curve model to capture those abrupt changes. Basically, we add a term gamma, gamma in this equation to capture the sudden shifts. And here, gamma, the value of gamma actually varies depending on the regime indicator S, which we modeled was modeled as a latent variable in our approach. And then we use a probability model to model the transition of the regime from one regime to the other. And we can also include predictors in the model to investigate what factors may have affected the probability of transitioning from one regime to the other. So here we include the intervention period, the intervention group, and then the interaction between them. And we also included 2 other dimensions of psychological well-being. First is relationship, and second is accomplishment. So with this model, we can answer like basically all the questions I have talked about in the previous slides, like the change of dynamic features, individual differences in these changes, both over period change and also abrupt change. And in the next slides, I want to talk more about the individual differences this model can capture. So first, as mentioned before, using the growth curve model, it can account for the initial level and over period growth rate of dynamic features. And then with the regime switching model, which aims to capture the abrupt changes, it allows the magnitude of abrupt changes from one regime to the other vary from across individuals, so that each individual, so some individual may have a very large jump to a higher IIV level or lower IIV level, and some others may have a very small jump. And also, finally, the timing and frequency of the abrupt changes or regime transitions. Because we are using the probability model, we didn't specify any known timing of the abrupt changes. Instead, we let the data tell us at which time this person transitioned to a specific regime. So that is all unknown and estimated. And we chose to use Bayesian modeling framework because of the following reasons. And the most important one is that because we are fitting a very complicated hierarchical model, and in which scenario this is the high dimensional integration is very computationally demanding, while Bayesian is can use the MCMC algorithm to approximate the numerical integration. So we choose to use Bayesian mainly because of this. And some bonus here is that Bayesian can also allow you incorporate some prior knowledge in your data. For example, if you already know that the variance is like in a specific range, or the inertia and the regulation level is in a specific range, you can add these constraints in your model. And finally, the Bayesian approach is very convenient to extract the uncertainty level around estimates. It doesn't involve any inference, but just extracting the summary statistics from the posterior samples. And Bayesian is also flexible in handling missing data, but this is not what we will be covering in this presentation. But it indeed allows you incorporate multiple models representing missing data regimes into the full model to account for the missingness. So this is the broad introduction of the methods. Below, I will use an empirical study to really illustrate what questions we can answer from this data and from these methods. First question we are interested is how did the three dynamic features change over periods within each group? And also on a between group level, we also would like to know whether the intervention groups experienced more increase in baseline or regulation or decrease in IV level compared to the group, compared to the control group, because we wanted to know whether there are indeed some between group differences to indicate the intervention effects. And for question 2, we also wonder if there are any abrupt changes or regime transitions in these dynamic features, and also if there are any group level differences in these changes. And finally, we are interested in whether the intervention group may have displayed a larger magnitude of sudden shifts. For example, it may have a larger jump from the higher regime to the lower regime compared to the control group. Next slide shows the key findings from this study. Note that we only have 2 groups here. One is the control group, the other is the intervention group 2, which received both positive and contemplative practices. This is just for illustration purposes. Certainly you can add all of the groups in your model. So for both groups, if you look at the plot on the right, we see a reduction, a decrease in their IV level, and also a decrease in their inertia level. And both of them indicate improved stability in their meaning of life dynamics. But we didn't find any credible increase or decrease in their baseline level. So if you look at the average level, you may not notice a very obvious change in the mean level on average. And we also didn't find that these changes are different between the control and the intervention group, which may indicate that the control group itself already, maybe by receiving the daily monitoring every day, they already have some, it already helped improve their psychological well-being with the daily monitoring. But more need to be investigated and discussed. So for example, we may not have captured some very important predictors in our model to really capture the between group differences. Again, this is just an illustrative model to show how the model works and what questions we can understand. For the next two questions, we did find some regime transitions in the IV level. And we found that some participants are more likely to switch to the low IV regime when they reported high level of positive relationships. So that means that being exposed to positive relationships may help improve people's feeling of meaning of life. But again, we didn't find any between group differences in the probability of transitioning to the low regime. And also we didn't find any between groups in the magnitude of their abrupt changes on average. Then next we look further into the individual time series. If you could go to next slides. So although we didn't find any very statistically significant group level differences, when we investigate the individual time series, we did find that some participants shows the transitions between regimes. Like for instance, participants 2 here, we can see that it first transitioned from the high IV regime, then to a low IV regime, and then to a high, and then to a low. And our model could capture these changes by the y-axis on the right, so which is the probability of transitioning to the high IV level. You can see that the shaded area is high when this person displays a high level of variance. So that means our model can capture the transitions and the timing of the transitions very well. And similarly in participants' force dynamics, at the beginning, you can see that the variance is high and our model, the shaded area is also high, indicating a higher probability of transitioning to the high IV level regime. Yes, I think that's all for the empirical study. And they further provided some guidance or suggestions for model selection. Because as you may have seen, we are trying to capture a lot of different types of changes, both gradual over period changes and also abrupt changes, and also individual differences. So people may want some clear guideline or a pipeline to what model I should fit, which model I should start with. So this diagram or flowchart basically shows our suggestions. First, we would like to suggest that you fit a random walk model to both the baseline regulation and IV and those three dynamic features. This is just to illustrate if to investigate if there are any changes over time in these three dynamic features. And if they are not, then maybe we don't need any time varying model. We just need to fit a model with time invariant parameters. And if you did find some over time changes, then a time varying parameter model is needed. We need to further investigate whether just simple time varying model quantifying the overtime changes is sufficient, or we need to add the regime switching component. And this also involves some diagnosis of involves using some diagnostic measures. So here we propose some diagnostic measures. The first is the inference about some K model parameters. In the model presented before, there are some K model parameters that represent the features that we are interested in, such as the growth, the slope parameter in the growth curve model, which capture the over period changes, and also that gamma in that regime switching model, which capture the sudden shifts. And all those are parameters of interest that we want to look at. And we want to look at both the practical and statistical significance of those parameters to help guide our choice. And then also we also use IC measures, which is widely used in model selection. So we also use them. The unique thing is that we also included entropy measure as the diagnostic measure, because we are introducing the regime switching component, and we may wonder like how many numbers of regimes are there in the dynamics, and whether the two regime model is necessary, is needed, is more like necessarily needed than the one regime model. So this entropy measure is widely used in mixture modeling, but not examined in the context of this model. So we did some simulation study to evaluate the effectiveness of this entropy measure. Next slide is the simulation study. We aimed at answering three questions. First, this is a very complex model, and we want to know like how many time points are sufficient to detect all these type of changes in the context of the proposed model. And also we proposed several dynamic diagnostic measures, and we wanted to know whether they are helpful for detecting the different type of changes, whether they are helpful in selecting the best model. And finally, we are wondering if the proposed research are sensitive to the effective size of the abrupt changes, whether it can capture both large and small abrupt changes. Okay, this is I'll go very quick on these slides because those are all technical details, and you may find it in our paper in the later publication. So we basically invested two sample size configurations. One is small and the other is large. The large condition is to mirror the settings in the empirical study, while the small one is to test whether a smaller sample can be already sufficient to fit that model. We considered both regime switching and non-regime switching models, and also regime switching models with different number of regimes, just to investigate whether our method can pick up the true data generation model. Okay, so the findings. So first, luckily we found that even with this small sample size, all the model parameters can be well recovered. So which means that if you only, although it's not, someone may argue that it's not very small, like in traditional longitudinal studies, but with EMA studies, since we we measure participants repeatedly every day or even hourly. So this is really a relatively small sample size in EMA studies. And for the question 2, we found that entropy, AUC, and inferences on the process noise variance parameters were more informative than IC measures in detecting abrupt changes or the optimal number of regimes, which means that if we only use IC measures to select the model, you may select the wrong model or the model with not optimal number of regimes, while the entropy measure gives you a more like informative information to help you select the best model. And it's a value ranging from 0 to 1, with 1 representing, with values closer to 1 representing better classification of different regimes. And finally, if you can go back to the question 3, yeah. So, and also our model can we can successfully select the regime switching model when there were indeed some regime transitions in the dynamics. And also, we can also correctly select the non-regime switching model when there are no abrupt changes in the dynamics, which means that our methods is kind of robust to both various levels of abrupt changes. Okay, so next, so there are some limitations of this work. So first, we have very strong assumption about the change pattern of these dynamic features. We use a linear growth curve model, which specify a known timing of change and number of change points, that is pre, during, and post intervention. And this is really a starting point or as an illustration purpose. People can also fit like more complicated models, like capturing the nonlinear change pattern besides just using the linear growth curve. And also there are some challenges in come up with the candidate models to capture the structural changes. Like in the regime switching model, we really need some more informative predictors to help predict the probability of transitioning from one regime to the other. And the prediction performance really highly depends on the selection of those predictors. And also, since we are fitting this model in the Bayesian framework, it takes longer than like when using the frequentist methods. For instance, it may take like 14 hours to run the model to the empirical data. But luckily, recently I was exposed to a Python package called PyMC, and it can fit. It can do similar things to like many Bayesian software, like Stan and JAX, but it's much more faster. It's much faster than Stan and JAX. So basically, with the same number of participants and time points, it can even finish the model fitting within 1 hour. So it's very, very large improvement of computational efficiency. So yeah, that's very promising. and I would definitely try PyMC in my later research. And finally, some key takeaways is we introduced the multilevel EMA data, and we introduced our methods to simultaneously quantify different type of changes in dynamic features as well as individual differences. And we would like to highlight that more advanced tools are needed to capture these changes, because the change pattern really varies a lot across participants, and every participant is unique in their change patterns, and we need to accommodate all of them in a more comprehensive modeling framework. And because of that, we also need more model selection metrics to help us select the best model. Okay, I think that's all for my presentation. Thank you for your attention.
All right. Thanks, Yanling. Are there any questions from the discussion or any clarification questions? If there are any, just unmute yourself. And so while the people might be getting thinking of their questions, I have a quick question. One is for people to practically be able to use this method that you develop, are there any software that they can actually, say that someone has collected data from, dynamic, like Apple Watches or something like that, and they have this different types of data that fits into your framework of multiple waves, right? Are there like software that they can actually work with your model, or not?
As far as I know, there are not existing software that can capture all the features in the model. I know that there are some R packages that can do Bayesian hierarchical modeling like BRMS, but that usually I think is already maybe very commonly used models without incorporating all of these different types of changes in the model. So yeah, it really needs you to manually specifying each equation in your model, and you need to write your own syntax in your Stan or JAX code.
I see. Okay.
But we
Is
do
that because
have,
you're using a Bayesian estimation approach, or is it that so more along the line that I was thinking whether that you are planning on making like an R package or a Python package that's publicly available for people to use, I guess.
Yeah, that can be done by maybe a Shining app or
Okay.
some encapsulating all the procedures in one Python package. Yeah.
All right. Okay. I do have another question. So your multiple waves. So from the example, at the beginning, I didn't understand what the waves are. So the question that I had at the beginning was whether there should be a gap between the two waves. But now that you said that pre-intervention, intervention, and then post-intervention, I guess these periods needs to be defined before. Does that make sense?
Yes. Yeah.
At the design stage?
Yeah, because it's a bit tricky because when it comes to multiple waves, people always think about like there are some time interval between waves. But in our illustrative example, it's consecutive time points.
Okay.
But yeah, we do want to highlight that the approach is can be generalizable to like the scenarios you mentioned when there are time intervals between waves. Because the key idea is really to model the changes in the dynamic features. It doesn't matter if there are time intervals or no time intervals between waves. Yeah.
So is that correct to understand that if they change the intervention, right? So for example, if they're like an adaptive intervention or something like that, it still can be incorporated into your model framework, the hierarchical framework?
Yes.
All right, sounds good. Any other questions, I guess? All right. If there's any questions, Yanling, can you include your email address so that if there is any other, like in the chat window, if there are questions for participants, they can reach out to you directly.
Yes.
If
Sure. It's also included in my slides.
Yeah, so we will share these slides as well as the recorded the link to the recording after the seminar with a feedback survey. So again, thank you very much, Yanling, for the great talk. We will see everyone in the next bird seminar. Have a good rest of the day, everyone. Thank you.
Thank you. Bye.